All right, so you'll see right here that we're actually pretty much to the end of chapter 2, and the last thing we're actually going to be talking about is densities. In case you're wondering, we actually have technically covered all the conversion factor stuff, okay? But of course, it is very much me working it out in front of you has actually very little value, okay? You working it out and finding out where your problems are is the value, okay? Yeah. If I had more time and less people in here, I could do something like that. But unfortunately, that's kind of rough. But that's why we have the lab. That'll be really helpful. Okay, so these are some different densities of common substances. You can all see these. For example, we have helium and hydrogen here. Anybody know what those are commonly used for? You put them in balloons and stuff, right? Or blimps. Like the Hindenburg. Bad example. Too soon? All right. So notice that those are lighter than air. See that? Yeah. And so why do you put them in balloons?
Because they float.
They're less dense than air, and so they float. Exactly. Yep. You both answered the problem. Exactly. Note you can do nitrogen, but it's not quite light enough to overcome the skin of the air. And have you ever seen those balloons that kind of bob and are basically equal to air? Basically, wherever you set them, they kind of stay there. Those are typically nitrogen.
Or if you blow them up with your mouth.
The ones that you blow up in your mouth are typically more dense.
Really?
Yes, just by low. Yeah, yep, exactly. That's why they end up falling to the ground. Yeah. If you get a thin enough skin of the right materials, you can actually blow them up with your mouth, and they'll just be about the same density. The problem being you're moistening the air. Your internal humidity is higher than the environment. Yeah. Yeah. So right here we see some different things. For example, here's water, and so you go to the gas station, you look at the puddles. What do they look like? A rainbow, yeah, like a shimmer on the top, right? And that's because gasoline is lighter than water, and so it spreads out over the surface of the puddles. And that makes that shimmery color. Which is very pretty, but is actually like horrible for the environment. Yeah. Anyways, so here's a condition. You knew this was coming back to some sort of healthcare thing, right? So this is a condition of severe thinning bone. It's known as osteoporosis. It may occur. Scanning electron micrographs, SEMs, these are what scanning electron micrographs look like after they've been processed by computers to make them more coherent looking to a human brain. Show A, right here we have a normal bone. Notice it's not perfectly even. There's little pits and stuff in it, damage, etc., imperfections, right? But it's pretty dense, right? Doesn't have gapping holes everywhere. And so here's a bone with osteoporosis. This is actually due to the loss of the bone minerals, and you can see they've been thinned out severely, right? And so if you were to look at these and compare their densities, which one's more dense? A, definitely, right? Yeah, big time. Okay. This is less dense, has less minerals in it. And part of what you're seeing, by the way, do you guys know what bone actually looks like inside? Is it solid up through?
No, it has bone marrow.
It has bone marrow, right? And it's more like a steel wool with the bone marrow in it. Does that make sense? Yeah. And so the bone provides a bit of structural integrity. The bone marrow then produces things like your red blood cells, etc. Yeah. You okay?
I don't know. There's something about bone marrow just freaks me out. It's so gross.
Did you know you can use it like butter?
Oh, God.
It's actually really good.
Oh, my God.
Yeah. It's fantastic tasting. Yeah. Oh, yeah. Oh, yeah. Yeah, bone marrow is actually really great tasting. Yeah. Anyways, now you guys have a whole different opinion of me.
Like pig bone marrow, you can use for a lot of different things.
Oh, yes. Oh, yes. Yeah, beef bone marrow and pig bone marrow are fantastic.
Dogs like to eat it, I know that.
Well, you can use it like a butter, honestly.
Yeah, yeah, it is like a gelatin or butter consistency. Yeah. So the bone density is often determined by passing a low dose of X-rays through the narrow top of the femur, which is your hip area, and the spine. Mostly these are due to the fact that these are high stress points in your body, and so it's just very important to understand the density of those, how strong those would be, right? If your spine cracks, you're going to have some problems, right? And your bone hips tend to take the most stress, even though they're one of the thickest part of the body. That's, if you're going to break something, it's going to be there. Yeah. So, and that's this right here, and you can actually see here the spine, right? Ooh, spine. Okay, so if you have something more dense, okay, what happens if I take 10 panes of glass and I squeeze them into one place? What happens to the light passing through?
It reduces.
Reduces, yeah. If I have a more dense fabric with a tighter weave, what happens to the light? It blocks more out, right? If I have something that's less dense, it blocks less, doesn't it? Okay? And so the same thing's happening to X-rays here, right? If I have a more dense bone, it blocks more of the X-rays. If I have a less dense bone, it blocks less. And that's why the X-rays can see through like your flesh, but they can't see through the bones easily. Okay? All right, so let's talk a bit about measuring density. Here we have a zinc object right there. I'm going to just tell you that most of the pictures of actual experimental stuff in this book are not done quite right. It's a weird thing. I don't know what it is. Almost every single one has something wrong with it. Like, for example, this is a weird way to measure that, right? See how it's precariously bouncing there, almost ready to fall over? Why? Like, why, right? You could have stood it straight up. You could have set it on side. There are so many things that could have been done, but yet. Anyways, you measure the mass of the zinc. You then measure the volume. Now, when you have an object that has lots of like pits in it and a weird shape, it's not always easy to measure that with like a tape measure, right? And so what you can do is you can use volume displacement. So we fill up an object like a graduated cylinder that can accurately measure the volume of something, okay? When we're going to drop this zinc rod in, it's right there, if you can see it. And then that difference in the volume is the volume of the zinc rod once you get all the bubbles to get off the surface, okay? You do have to like tap it and you get all those dang bubbles to get off because they do take up volume, right? Anybody know where this came from? At least in the mythology of it. Anybody ever heard of Eureka? Yeah. Yeah. So the story of Eureka is that he was trying to measure the the density of a crown to figure out how close it was to gold, or if it was diluted and not very close to gold. Okay. One of the tests you can do that is measuring density, because gold has density. If you put things like silver in it, or copper, or tin, or whatever, it'll change that density. Okay? And so he was trying to figure this out. This crown has, spikes on it, and it's all decorative, and it's beautiful looking. So you can melt the dang thing down and cast a brick, right? And then you could just measure it. But then all the beauty of the crown is gone. And there goes the crown. And so he was racking his brain, couldn't figure it out. So finally his wife goes, "Go take a bath, you stink." And he goes, takes a bath, he lowers himself into the water. What happens to the water in the bath?
It goes up.
It raises
Goes up. And how much is it displaced by?
the mass of him.
The volume of him,
The
right?
volume of him, I'm
Yeah.
sorry.
No, you're good. I knew. Yeah. Freudian slip. And so, yeah, it's if you submerge an object into a volume of water, the volume changes depending on the volume of that object, right? And so he jumps out of the bath, Eureka, and runs down to the palace naked. At least that's the mythos. Okay? And so it makes for a very good story. Probably didn't happen like that, but great story, right? Very fun. Anyways, this is density. And so we take that mass in grams from the weighing it right here. We divide that by the amount of displacement for the volume. Now again, that difference, the initial volume versus after you put the zinc rod in, that's that displacement, right? That's that difference in volume. Okay. You can do this down at the bottom if you want, or you can do this independently when you're doing these measurements here. You just take the difference, so the final minus initial. Okay, and so you see that our volume is actually quite inaccurate compared to our weight measurement, isn't it? Yeah, 2 sig figs versus our 4 sig figs up here. That's very, very common. Most balances can do 2 decimal places to 4 decimal places, and those are quite cheap actually. You can get those for like $50 for your kitchen.
So why did you put it in 2 sig figs at the end?
Because it's the least accurate measurement that always sets your number of sig figs.
That's with like addition and subtraction, right?
Yep, that's the least number of decimal places. Not sig figs, but decimal places for those. But so that was due to the fact that when you add, you're going to maintain your decimal places.
Yeah, and then you draw it.
Exactly.
I learned that.
Yep. This is multiplication division, so it's sig figs because when you have a very small number, it changes things massively in multiplication division, right? Whereas you add small numbers, they change it very little. Okay. And we get finally a density. Most densities are quoted in these grams per milliliter. So John took 2 teaspoons of cough syrup for a cough. If a syrup has a density of 1.20 grams per milliliter, and there's 5 milliliters in 1 teaspoon, what would be the mass in grams of the cough syrup? Now, just to make sure that you understand something, unit conversions and being able to do that where you just convert one unit to another, to another, to another, there's actually very little memorization that has to happen in this course. Okay? You just need to understand if you eliminate one unit and go to another, you can do that. And you need to be able to do that over and over and over. Okay? Almost every problem that's math-wise can be handled by that methodology. Okay? All right, so let's go ahead and try out this problem. What do I have? What do I need? How do I get there? So what do I have?
The density.
Yep, I have the density. That is exactly correct. Okay, and so I have my density right there. Okay, what else do I have?
You have the amount that he took.
I have the amount he took, 2 teaspoons right there, don't I? Okay, and I have one more thing. This right here is a conversion factor, isn't it?
Yes.
Yeah. I can rewrite this as 5.0 milliliters over 1 teaspoon, can I?
It can't be 1 over 5.
It can.
It can? Okay.
Yeah. Yeah, you can express it either way. You could also express it as an equality, okay? Which would be 5 milliliters equals 1 teaspoon. So that's why you can do it either way, is the equality is those equal to each other. And you can divide either one over, right? Yeah. Does that make more sense-ish?
I would have to see it.
Okay. So that's just 5 milliliters equals 1 teaspoon. And so whichever way I want to end up in, I can just divide either side. Okay. Or another way of thinking that, I can always flip a conversion factor or one of these ratios. I can always flip that as long as I take everything in denominator and put it in numerator and vice versa, right? Okay. Okay, it's that. You can do the same thing to both sides in math. So finally, we need to go, where do I need to be, right? And what do I want to be?
You need mass in grams.
Yep, mass in grams of that dang cough syrup, right? Okay. And so I would express this out when I'm starting to do these problems. Cough. I'm just going to put cough. Okay. And the reason I would fully express things out when I'm starting these problems is because if I get the wrong units at the end of this, it gives me a double check. Do I have grams? Oh, no, I didn't. I wasn't in grams. Okay. Many of you have probably had issues with this, especially where it's like grams versus milligrams, right? And then like I got the problem wrong because I didn't convert it into milligrams. Damn it. Yeah. Okay. So again, this is just that in case you forgot it. Expressed out on a slide. Note, these are the conversion factors I was talking about, and their equalities. Just expressed all the different versions of that you could have.
Show us how to like convert it over, like how to actually work it out.
Yeah, I'm going to do the full conversion in just a bit here.
Okay.
Yeah. Yeah, I'm just showing you the conversion factors,
Okay.
which you can express. For example, this is already expressed as a conversion factor. Okay? It's 1 gram over 1 milliliter, right? Mm-hmm.
So you could just do like knowing the 2 teaspoons. If you multiply the 2 times the 5 is 10 times the gram or the milliliters, get rid of milliliters, then it's just 12 grams.
Yeah.
Okay.
Yeah. So let's go ahead and do it expressly though, because
Those are gonna be hard ones.
yes, and in general, it's just a good way to, when you're setting things up, not make mistakes. Okay, and some of you probably need it expressly done because you're just not sure about what's going on. Okay, so again, I'm just expressing these conversion factors, these equalities that were in the problem that were given to me. Okay, this one right here is that teaspoon over milliliters that we were just talking about, right? This one is actually the density. So that density right there is that one. Okay? So densities are also equalities, right? Because they're conversion factors as well. Okay. Now, yes, and so we go ahead and we go, let's see, we started with 2 teaspoons, so we can go ahead and go 2 teaspoons first. Okay. Mm-hmm.
Are you going to give us conversion factors for exams, or are we expected
Nope.
to bring those in with us?
You're going to be expected to bring those. Yep. Now, I will give you some that are like really off the wall weird ones. But, yeah, you're expected to bring most of the really standard stuff. Okay? And probably your best bet is if it's a conversion that's very common, like imperial to metric, or if you need your prefixes, which ideally you'd have in your head. But, yeah, that sort of thing. Let's see. So we're going to go ahead and get rid of teaspoons. So what we need to do is use the teaspoon conversion factor. And again, you always want to go, how do I get there, okay? So I have teaspoons starting off with. I need to get into grams, don't I? So I look at this and I go, grams are right there. Okay? I don't have a teaspoons to grams, do I? No. So I need to get into milliliters, don't I, first? I have a way of going from teaspoons to milliliters, don't I? This will get me to milliliters. And then I need to go from milliliters into grams. Okay? And you see I'm just making myself a pathway. I'm now going to try to follow that pathway. And so I'm going to take teaspoons. I'm starting off with that. Mostly I'm starting off with that because it's not divided by anything. So it's easy to figure out which side needs to be on top. Yeah. And then I'm going to take and I'm going to get rid of teaspoons. So teaspoon needs to be on the bottom, right? Because teaspoon divided by teaspoon is going to cancel. And on top, I need to be in milliliters. Okay. Why do I group these two things up and I don't go into grams somehow magically? I don't have anything that's a ratio that would get me into grams from teaspoons, do I? No. And so I have to go into milliliters. I don't have any choice. I don't have any other options. Okay? Okay, the next one I'm going to do is, well, I have milliliters right now, don't I? And so I'm going to get rid of milliliters by putting milliliters on the bottom. And then I have something that relates that to grams, which is the density, right? And so I put grams up here. I have to fill in those numbers. Don't forget this number of grams is connected to that grams. Okay? I have to move those together. All right. Now, notice that this is going to cancel everything out but grams, isn't it? And that will leave me in grams. I know I'm going to get the right answer. I just have to go through this times this times this divided by 1, which is the same thing.
But you have to divide by one.
You don't. Yeah. I'm just expressing that there are ones down here. Dividing by 1 doesn't do anything.
Yeah.
It's just to get rid of the milliliters.
Yep. Yep. Okay. Anybody have any questions? Anybody get lost in there?
Start
Please.
with 2 teaspoons, because that's the smallest conversion unit, and then you go.
I start with 2 teaspoons because number one, it's what I took and have at the beginning. But the other part is that it simplifies things because it doesn't have a divided by another unit. And so there's not really anything else to mess with. Okay? And what I do here is, let's say I messed this up, okay? I completely botched this. I should have started with 1 over teaspoon or something. Okay? I'm not going to get grams out at the end of this, am I? I won't be able to cancel that into grams. And so what would happen is I'd be going, I can't get rid of teaspoons and get into grams. And so that would tell me I need to flip things, don't I? Okay? If I tried to do this exact same conversion, but it was 1 over teaspoons, I'd end up with 1 over grams when I tried this. Okay? And if I ended up with 1 over something, and I wanted grams at the end of this, and I ended up with 1 over grams, does anybody know what I need to do? So if I end up, let's say I do this upside down by accident. I messed up on the first one I chose, and I did that upside down. So
1
I messed
over
up.
5.0 milliliters like that.
I would end up with, okay, so let's step backwards, okay? How do I know to put a 2 teaspoons here and not a 1 over 2 teaspoons? Or start with this? Or start with the density? How do I know that? I don't. I don't necessarily know that. Okay? I could be mistaken. It actually happens. And it'll happen a lot. Right? And so, if I do this procedure where I cancel out units every time, then when I get to the end of this, I'm always going to have what the units play out as. It's always going to be what they are. And what will happen is, if I mess this up, I'll end up in something like 1 over 12 grams. So if I messed up and grabbed the wrong thing to start with, I'll end up with 1 over my answer. Because I'll still be moving towards grams, right? I'll just end up in 1 over because I selected the wrong one. Okay? And so what happens is, if I end up with an answer like that, that's not the correct answer, is it? And I know it's not the correct answer because I had those double checks throughout the way, right? Okay. Anybody know how to fix that, by the way? Yeah. Now all you gotta do is just take 1 divided by that number. So if I go like that, that will flip that over. Yeah. Alternatively, I can just flip my entire equation. Okay? Okay. Anyways, work a problem. You'll encounter it eventually. You'll start with the wrong thing, and you'll end up with the inverse of what you should have gotten, right? If you started with density here, that's a pretty common way to mess up, okay? Okay, so let's talk about specific gravity. SPGR is the abbreviation to that. So this is a relationship between the density of a substance and the density of the water. Basically, it's just the density divided by the density of water. Now, the density of water is a value that's extremely close to 1, wherever you are in the world, okay? It's usually 0.999 something. And so the density, specific gravity, is not very different than the density of water. Specifically, the density of water would actually round to 1 at 4 degrees Celsius, in case you're wondering. So a substance with a specific gravity of 1 has the same density as water, and you would expect if you put it in water for it to just sort of bob around at whatever level you put it at. Okay? If it has a density that's greater than water, what would you expect? Sinks, yeah. Like a lead weight, right? If it has a density that's less than water, what would you expect? Yeah, float, like a cork or something, right? Or like a balloon. Or like a buoy. Does anybody know how boats work? Yeah, they kind of mimic density by increasing that surface area that's in contact with the water. Okay? It's a little bit more complex than that, but I don't want to get into the math, so we'll leave it at that, okay? Okay. So this is actually an application of this. This is a hydrometer. It's used to measure the specific gravity of urine. The normal range of specific gravity for urine is actually 1.003 to 1.030. So if you put water here in a urine, what would you expect?
The water to rise to the top.
Yeah, very slowly though, right? Yeah. So it's going to be a very small difference, and you should see the water sort of float up just very slowly, okay? But if you put a little bit of weight in it, you can actually adjust that so it just stays in place, okay? So the specific gravity can decrease with type 2 diabetes, kidney disease as well. It'll increase the specific gravity with dehydration, kidney infections, or liver disease. Okay? And so you can get an idea of what you might need to test for. And it's a quick and easy test, very low cost. Okay? It can get even lower cost and even quicker and easier. And so they've actually made what are called dipsticks right here. They contain chemical pads. They're used to evaluate the specific gravity. You can also include things like pH measurements on it to determine acidity, test for ketone bodies as well. And so it's very, very useful tool. Okay, that's why you're always getting asked to go pee in a cup when you go to the doctors. They always want your urine and your dang blood, right? And that's why. Your urine's actually incredibly useful to determine this. Probably in about 10 to 20 years, once the testing comes out and they start having like wide rollout and cheap methods to do this, they're probably going to start testing your fecal matter too. Okay? Because your long-term health it's probably the third largest determinant of your long-term health. Yeah. Yeah, you know what all the billionaires are getting done now?
Colonoscopies.
Kind of. They're getting fecal transplants.
What?
Because it can reduce your age, your biological age, by about 10 to 15 years. Yeah. Yeah.
Wait, serious?
Oh yeah. Oh yeah.
That might be the first time I've heard of a ridiculous medical treatment that might actually be worth it.
Oh, it is ridiculous, and it absolutely works. It totally works.